Christian Aparicio here again to give you another tutorial with Nastran Solution 200. My contact information is here. If you have any questions regarding Nastran Solution 200, please feel free to reach out to me. And for the remainder of the video, I'll just keep my email in the bottom right hand corner. Now, in this video, we are going to introduce a constraint. In the last video, we performed a unconstrained optimization example. We defined our surface plot that you see here. We defined our our design variables. And then at the end, we saw that what the optimizer did and found the minimum as 0,0. In this example, we are going to repeat the same process, but we're going to introduce a constraint. We are going to define a second equation. This is going to be called the equation constraint. And here it's going to be represented by this green ellipsoid that you see here. This green ellipsoid is defined as y1 squared plus y2 over 2 all squared. We are going to start at the same initial point, but we're going to say that whatever y1 and y2 are, this inequality has to be true. G1 evaluated should always be greater than 1. So we are saying that when the optimization occurs, any value outside of the green ellipsoid, any value greater than 1 is an acceptable or a feasible design. Here, this is what we should expect. We should expect the optimizer to go down towards the minimum. Once it encounters the constraint, it should stop going into the infeasible region. This is defined as the region where you have violated constraints. It should not go into the infeasible region. It should remain at least in the boundary of the feasible region. And here you see that's what happens. It goes towards the minimum. It eventually reaches the boundary of the feasible region. So then it follows along the boundary until ultimately it lands at a minimum that you see here. Let me see if I can get this plot to show me what the minimum is. So let's go here and take a look at what my minimum is. And here, by the end of the video, I should land on the value of y1 equal to 1 and the value of y2 equal to 0.05. So here, if I can get this to work, here's ultimately our minimum, 1, 0.05. And the surface value we should expect is a value of 1. So let's go ahead and go through the procedure with the web app. Here in the video description below, you'll find a link to the solution file. Feel free to download that file and follow along with me. Now, when you download the solution files, what you can do is select previously done work. So here, for example, I already have PDF files from a previous example I did. So I'll go ahead and select both files and then I'll upload it to the web app. Here you'll see that I've already defined my equation objective. So here, y1 squared plus y2 squared. My design variables, y1 and y2, at initial values of 3 and 4 have already been created. But the one thing we have to create for this example is the constraint. Here again, we're saying that G1 should always be greater than 1. So let's go ahead and define that in the web app. So for this, we'll go ahead and go to the constraints. And if you scroll down to step 3, mark the checkbox here. This is where you can type in or create an equation constraint, and then you can type in your equation function, or your constraint function rather. So here, y1 squared plus y2 divided by 2.0 squared should always be greater than 1.0. So now that we've done this, let's go ahead and move over to the exporter. Again, the web app generates all your Nastran entries for you. So here I have my variables, my equation objective, and my equation constraints. I'll go ahead and download a new version of this zip file. You might get a confirmation request, so let's go ahead and mark that as keep, and let's go ahead and extract this new file. And while this is happening, let me just reiterate what we expect to happen. So like before, we are going to start at a value of 3, 4. So that would be this red point here. The optimizer will try to find the minimum. So it's making a pass towards the minimum. Once it encounters the equation constraint, remember, the feasible region is outside of the ellipsoid. Once it hits the constraint, it's going to move along the constraint because it can still further minimize the objective. Ultimately, we land at a value of 1 and 0.05. So let's go ahead and start this optimization. So here we'll go ahead and get a summary of what's going on. This example should go relatively quickly. Just a quick reminder that if you have any questions regarding Nastran Solution 200, if you are a professional engineer, if you're a student who's starting with optimization, you are welcome to contact me at this email address. Now, let's go ahead and look at the objective function. Here you see that we start at a value of 25. So here, like before, we're starting at the initial value of 25, but eventually we hit a value of, let me see if I can see what value it is. We eventually hit a value of 1.56. So let's go ahead and take a look at what's happening there. So 25 down to 6.25 and then down to 1.5625. You'll notice that the objective ultimately lands at the value of 1. So this matches the minimum that we have in the plot. So here you can imagine this x value is that value of 1. So here it reached convergence at a value of 1. If we look at the design variables, we see that we start at values of 3, 4, and then we eventually land at a value of 1 and 0.05. So this matches exactly what we have here in the graph. Now, let's talk about the normalized constraints. Before, the normalized constraints were NA, indicating an unconstrained optimization was performed. This time we have the following. For the initial and for the first design cycles, there is no constraint value. You see it's blank essentially. It's when you hit design cycle 2, that's when we have a normalized constraint value. So for the initial and for the first design cycle, it's performing an unconstrained optimization example. And that is because these points are so far away from the constraint that it's not worth taking them into account during the optimization. It's not until you get close to the green ellipsoid that the constraints become active. That's when you see the normalized constraint values start to show values. So the optimizer detects that you're getting close to violating a constraint. So now it takes into account the constraints. Here we start at a value of 0.1875. If you have a positive normalized constraint, that means you're violating your constraint. And here that's exactly what we see. We see that the path the optimizer is taking has breached and gone into the infeasible region. This is the region that's violating this inequality. This is why the normalized constraint value is positive. Now, what happens after that, the optimizer brings you back to the boundary of the feasible region. So now you have a value close to 0. Here we have negative values for the constraints. Again, these are normalized constraints. A negative value means you're satisfying your constraints. So here you can see the optimizer is consistently at a normalized constraint value of 0, this means that you are essentially moving along the boundary of your constraint. So that would be these points along the green ellipsoid. So let me go ahead and open the graph again. So that is an example of a constraint optimization. Remember that the way to differentiate if an unconstrained or constrained optimization is occurring is by looking at the normalized constraints. If you have NA or if you have empty values, that means the optimizer is performing an unconstrained optimization. This could be because your constraints are very far from being violated, so the optimizer is saying, I won't even take into account the constraints just yet. The alternative is that maybe somewhere along the line the constraints were not applied to the optimization. But once the constraints are close to being violated, that's when the optimizer begins to take them into account. Here you can see that happens around the second design cycle. Now, what's going to happen in the next tutorial? The next tutorial, I believe, we'll be talking about side constraints. So here, let me pause there, and I'll see you in the next video.